Hello everyone, and welcome to the Physics Hour, a weekly event to explore different fields of research in physics and ask leading scientists some of your burning questions. My name is Simone, and we also have Eduardo here to help with the Q&A after the talk. Before we begin, many of us are likely to be tuning in from different places, but I'm from Montreal, which is situated on the land which has long served as a site of meeting and exchange amongst Indigenous peoples. I acknowledge the diverse Indigenous peoples whose presence marks this territory from which I'm joining you today, such as the Haudenosaunee and Anishinaabe, and encourage everyone to learn more about the land that they live and learn on through the links posted in the chat. The Canadian Association of Physicists is the voice of Canadian physics, representing physicists in all parts of their careers. The CAP provides leadership and support to the Canadian physics community by celebrating Canadian physics achievements, keeping members up to date, and by running various initiatives like the ones you see below. The CAP Student Advisory Council was formed in 2019 to create a strong student voice within the CAP. We are an egalitarian, diverse, inclusive, and action-oriented group which seeks to represent, support, and unify physics students across Canada. Some initiatives we're currently working on include advocating for increased student funding, advertising student opportunities through our website and social media, and interviewing physics students across Canada to understand how we can best serve the community. If you're interested in learning more about what we do, I encourage you to browse our website. We represent all physics students in Canada, so please get in touch with us through email or social media and share your voice. Now I'm pleased to welcome today's speaker, Professor Lindsay LeBlanc.
Thank you so much. Let me begin by sharing my screen and then I'll get into the talk here. It's my great pleasure to be here with you all today, and thank you so much for the invitation to give this talk, both to those who are here live in attendance and to those watching the recording later. My name is Lindsay LeBlanc. I'm a professor at the University of Alberta. We're situated here on Treaty 6 territory in Edmonton, Alberta. It's a traditional homeland of many different First Nations, Métis, and Inuit peoples whose histories, cultures, and languages continue to enhance our vibrant community here in this part of Canada. I am an atomic physicist, and so I'm going to tell you today about some of the work that we've been doing in my lab, but also maybe some more general ideas about what quantum technologies are and how we can use them and how we use atoms to explore them. So I would encourage you to ask questions. If there's anything burning while I'm giving the talk, please maybe alert me. Otherwise, I can try to leave a lot of time at the end of this talk to answer questions and just have a conversation with you about anything that's interesting to you. I've dropped my email address and website for our group here. They'll be again at the end of the talk, and I do encourage you to reach out if you have any questions, interested in research, anything like that. So let's dive in. I think a good place to start is to ask the question, what is quantum? It's a word we're actually hearing more and more these days. And it has a lot of different definitions. So if you go to pop culture or scientific fiction, quantum gets thrown around as a word. It's just any technology, any ideas that are too difficult to explain. And I think, that irks us as physicists. So it's good to dig in a little bit deeper. Another place it's used is in the news a lot, and uses this phrase called a quantum leap, also the name of an old TV show, I guess. As a substantial or paradigm shifting change. And they have the essence of it right in that quantization means that it goes from one distinct thing to another distinct thing. But often we think of quantum leaps as actually being very small. So I don't really love this definition either. And so you can see it in search terms. This is from a paper. I gave a talk this day a few years ago, but just left it on the slide here. It's used a lot. Really what quantum means is something about a new kind of science that was developed in the early 1900s. And so people then started to realize that there are many different physical quantities, but in particular energy that is quantized. And that means it comes in discrete bundles, sort of like I was mentioning on the last slide. So we use this language where one of the bundles is a quantum and several are called quanta, and they're really, really small. So just as an example, if you think about photons, which are the quantized units of light, then one little Christmas light here will output maybe typically, a watt of energy. And one of those photons is going to have 3 say 10 to the minus 19 joules. And this is where the sort of power of big numbers comes in. That means that in 1 second, this little bulb is going to emit 10 to the 18 photons, which if you write it out, looks something like this. And that, it gets to be really, really big. And that sort of is hard for us at the human scale to understand when we start adding that many zeros to something. However, that sort of discreteness is the flavor of what we want to grab onto here. And I think this tweet from a few years ago too answers the questions well. What do the words quantum mean to you in one tweet or less? And Catherine, who's actually an atomic physicist as well, but also into comedy, says that it comes in packets. And there's, this dishwashing liquid, that these little tabs that are actually very convenient because you just have to throw one in, exactly how much dishwashing liquid to use. But they're also quantized and they have the name quantum. So I thought that was pretty funny. So in a more scientific, rigorous way, what does it mean? We can think about things that are on different length scales in our universe, ranging from, the size of the universe at 10 to the 28 meters down to the scale of human beings at about 1 meter. And you can see that that's why we chose a meter to be our standard unit of length, is because that's what we interact with. And then we can go much smaller, down to the viruses that we're also familiar with now, down to the scale of atoms, nuclei, and quarks. And really, when we're thinking about quantum things, we're kind of on this scale down here. So we're in the quantum regime when things are typically below about a micron. And the sort of lower you get, maybe the more quantum it is, but down at the scale of atoms, things are very much quantum. And it was really this discovery of the atom alongside thinking about things like black body radiation, but the sort of discovery of the atom and atomic physics, which is the field that I work in, really developed alongside quantum mechanics. And for that reason, atoms are really just the quintessential quantum object, and they're really great to work with. Part of what is interesting now, what's going on with technology, is actually trying to push this regime higher so that we can actually, as human beings, interact with things on the quantum scale. And so that's sort of when we're talking about technology, what are those limits? How far can we push this so that we can actually use these quantum effects for something useful? So there's this nice paper, it's actually talking about something called quantum sensing, published a few years ago now. And it actually divvies up the idea of quantumness. This is a word I've made up, but other people use as well. And how quantum something is. And so there's actually sort of 3 different levels that we can think about on how the quantumness affects what's going on in terms of the physical behavior. So in the first one, I've just rewritten this on the side here. We use a quantum object to measure a physical quantity, either a classical or quantum. And this is characterized by quantized energy levels. So this is maybe what you would first think of when you think of something quantum, is that it has these discrete energies. And being an atomic physicist, I'm going to give you an example of an atom, for instance, well, some 6 nucleon atoms, say lithium, for example, and it will have some electrons on the outside. And those electrons can only take certain orbitals. And so you've seen this in chemistry, maybe you see it in early quantum mechanics courses, where you go from having an electron orbital that's completely spherically symmetric and round to one that has this sort of dumbbell shape. And we call these the S and P orbitals, or the L equals 0, L equals 1. But there's a discrete difference between these, and this one has a lower energy than this one. And that kind of quantumness is maybe the first level of quantization, is that you get these discrete energy levels, and they're associated with discrete changes in some physical quantity. In this case, it's the orbital angular momentum of the electron. So that's actually going from 0 units of angular momentum here to 1 unit of angular momentum to 2 units of angular momentum. And to be perfectly honest, Bohr and his model of the atom had that idea down pat. When he thought about the different sort of wavelengths meeting around the atom, he had the same idea in mind of this discretization of angular momentum. And that's a very correct idea, even though the picture of atoms orbiting around nuclei is wrong. As we know now, the idea of that quantized angular momentum is very correct. So that's kind of the first level. And a lot of technologies that we know and use today use quantumness on this level. So for example, transistors, the many billions of them you carry in your pocket in your phone, rely on the quantization of energy levels to operate. CCD cameras are another very prime example. Lasers. Many of the technologies that have been developed over the last, say, 60 years do indeed rely on this level of quantumness. And so as we're talking about something called the second quantum revolution right now, what we're really talking about is moving beyond this to the next levels of quantum mechanics. And so the second one might be considered the use of quantum coherence. i.e. the idea that you can have a spatial or temporal or any kind of superposition of this physical quantity. And so this is written out in sort of this quasi-mathematical language here, where we can think about an object, say this lithium atom we had from before, being in both this S level and this P level at the same time. And so we mathematically consider this, object altogether to be the state of this atom. And we represent that by having some numbers, which I'm just representing by A and B, as well as something called the phase, just representing that these numbers can be complex. And so, instead of using these pictures, we represent these just with zeros and ones. And so in this quantum object, we now have more information. We have amplitude and phase information. So we sort of have two pieces of information that we're carrying along in one physical object here. And this is the power behind quantum computing, for example, and the idea of a qubit, that you can carry more than one piece of information in one physical object. And that's the sort of, exponentially the exponential power of quantum computing comes from the fact that there's these additional degrees of freedom in one single atom. And you can sort of see that in the fact that there is this, we can have complex numbers describe these things, and that, complex number holds two pieces of information as well. So it's sort of another way to see the same thing. So this is the second level where we can have superpositions or quantum coherence between our objects. And then the third one is called quantum entanglement. And so this is where we can improve our system in terms of, say, sensitivity or precision beyond the classical limit. And quantum entanglement really means even something more than superposition. And it's a little bit hard to understand, so I'm just going to give you a flavor here. But now imagine you have two objects of, say, a purple and a blue atom, just giving them colors to distinguish them. But what we're saying is that we can set up a situation where if the one atom is in the first state, what we'll call 0 here, or what we called the S state earlier, then the other atom also has to be in that state. Or it is going to, if it's in the first excited state, this P level, which we'll label 1, the other one also has to be in 1. And what we're saying is you cannot find 1 and 0 and 1 and 1. They're either they're always both the same as zeros or both the same as ones. And this is just one particular example of an entangled state, but this is an interesting state because it is what we call non-separable. You can't sort of factor this state out into a state of this different superpositions. This is it. And this kind of entanglement leads to some of this sort of spooky action at a distance quantum effects that you might have heard about. And it also leads to the sort of power of the cryptography or the secure information that happens with quantum information, because in a way, if you know what one thing is doing, you already have the information about the other, and that lets you do some interesting things. I'm not going to get too much into that. That's not really my area of research, but it is a very powerful resource that is available in quantum systems. And this is really what a lot of research is looking at, is how can we exploit this really cool effect about quantum mechanics to do interesting technologies to learn more about our universe and everything that goes along with it. Actually, there's, the black hole scientists really are interested in entangled states too. Idea of if you send one of these atoms into the black hole and you lose all the information, what happens to the other one? So there's very fundamental questions you can ask, and also very practical questions like how much information can I send through my credit card to get secure banking? So the kind of questions that I am interested in come about using these quantum systems. So one question is, how and when does the many quantum systems acting together give rise to new behaviors? And so everything from magnetism to superconductivity actually is described by the quantum behavior of atoms at the individual level. And part of my research that I'm not really going to talk about today focuses on how we can understand that macroscopic behavior of many particles together, starting from the foundations of individual particles, sort of building up these systems from the ground up. The other hat that I wear is maybe a bit more technological, and that's the one I'm going to talk about today, asking the question about how quantumness of atom scale particles, the ones that I use in the lab, can be harnessed and brought up to the human scale, as if we could actually hold an atom, but where we can actually develop practical technologies that use these quantum effects to do interesting and useful things. So these technologies can be sometimes classified in 3 categories, sometimes 4 and sometimes 5. People have different definitions of this, but these are pretty broad categories. So first, you might have heard of quantum computing, and quantum computing can be very powerful because it has this opportunity to do not more powerful computing necessarily than the kind of computers that you're used to, but it can do it differently. And because it does it differently, it's good at different things. And so I think we'll always have classical computers, and we will also have quantum computers, and they will do different things. Things that quantum computers are good at include factorization, and that's important for security because much of our security right now is based on the ability to factor prime numbers, or the inability of computers to factor prime numbers rather. And because it's so difficult, we just say, oh, it has to be secure. But if a quantum computer came along, it means that it could actually break this current security paradigm, and it means we have to think of new things to do. Quantum computers are also very good at optimization. So this is sometimes called the traveling salesperson problem, or grocery delivery, you can think of it as. If I want to go to all of these houses, what is the best path to save gas, basically? And it turns out this is actually a very difficult problem classically to solve. Quantum computing is also very good at searching. So if you have a long list, a database, and you want to look a particular thing up, it's good at finding it. And maybe more along the lines of this fundamental research, part of my lab is quantum simulation. So the idea of using quantum systems to actually compute what happens in other quantum systems. And that can be very powerful as well. So that's computing. Communications is more what I will talk about today. So there are a number of different sort of schemes for perfectly secure communications, which means that you can't have any kind of eavesdropping. You can't tap the signal off as it goes from one place to the other and listen in, because you will always know that that's happening. And you can if you can detect the eavesdropper, then you just throw out that signal and you say, don't listen to that, and we'll wait until we get a secure line. And so there's sort of a perfect security that can happen with quantum systems that it can't happen with traditional classical systems. In terms of sensing and metrology, this is something I'll talk about a little bit as well. Quantum systems are very good at interacting with other kinds of things around them, and they're used for different technologies. For example, right now they are used in the global positioning system for precision timekeeping. So there's a little atomic clock aboard every GPS satellite, and the better we can make those clocks, the better we can actually do sensing and locating things on the ground, although it's pretty good already, I have to say. Other applications include sensitive magnetic field detection, including for biological activity. So there's actually a recently formed company that looks at brain imaging from the magnetic fields that your brain puts out. So you can actually just wear a helmet instead of having to lay inside of an MRI machine, for example. A friend of mine actually did fetal heart monitoring using atoms. So you can put one of these atomic magnetometers on a pregnant person's belly and actually see the fetal heartbeat at that range. And then also calibration of other electromagnetic signals. It can be very useful. So these atoms are very sensitive to so many things. And if we can detect at the quantum level, we can look for very sensitive signals. And using entanglement, we can actually hope to do even better than we can right now. So there's a lot of potential on these different technologies. And I just wanted to sort of put that out there and just say to all of you, I think it's a really exciting field. There's a lot of funding right in Canada right now for it. And if you're interested in it, I think there's a lot of opportunity. How I find myself here, I think it's actually fun when I give undergraduate talks, because I like to sort of recall how I got myself here. And it started actually in the spring of 2000. I was an undergraduate student here at the University of Alberta, where I've ended up. And I was in engineering because it seemed like engineering was the practical thing to do when you liked math and science. But I was pulled towards the sort of physics side of things because we had this program called engineering physics. And the thing that really stood out to me was a third-year course that I was able to take called quantum mechanics. And it was just, I don't know, so fascinating to me. And I really wanted to take a course on quantum mechanics while I was at university. And that really pulled me into the engineering physics stream. And it turned out to be absolutely the right choice. And I really liked the program because I got both sort of the engineering side and the physics side of things. And I, as you have figured out, eventually ended up in physics. But it was a good sort of way to start that. But it was really quantum mechanics that pulled me there. And, you know, I got to study that. This was my textbook, which I still use pretty frequently. The early edition, let's say, of Griffiths, which many of you probably use. And I also did a lot of lab work when I was an undergraduate. So these are a couple of photos of me, actually the very first digital photos ever taken of me in the winter of 2002 when I was an undergraduate student, and we got a new digital camera for our lab to do some data recording, and nobody had ever used a digital camera before in my class. So they went around and took pictures of us all, and this is the results of some of that. So basically what's happened is now 20 years later, I'm still doing quantum mechanics. I still think it's fascinating, and I love both studying it, I love teaching it now too. And you know, it still holds that same kind of fascination for me as it did 22 years ago when I was deciding what to do with my university career. So, you know, that doesn't happen for everyone. People change their minds and they end up doing different things. And my path has been very varied as well. But you know, it has been sort of the thing that has been constant throughout all of the things I've done through my life. So going back to the physics a little bit, how can we actually use atoms to harness this quantum behavior? And as I was mentioning earlier, atoms are really just such a perfect quantum system. How can we use them? So there's different kinds of systems we can use. The ones I like are these free atoms and molecules, but there's also a number of different kind of solid state emitters. So there's a number of groups in Canada working on this. So this is representing what's called a nitrogen vacancy center. So it's sort of like an artificial atom inside of a solid. It's very much like an atom. Semiconductors can also be used, kind of like the transistors that I was telling you about earlier in your pocket. And then we need some kind of interaction to interact with these matter systems so we can encode the information in light, either by its frequency. So you can have like, sorry, long wavelength versus short wavelength, and it can be, you know, optical, it can be radio frequency, it can be microwave. There's always all different ways to interact with things. We can have different polarizations act as sort of one state or another with light. And we can also have timing be what we call our qubit. So whether the pulse comes early or late, that could determine what kind of quantum state that that these material systems are actually holding on to. So there's many more. Phase is another one, for example. It's hard to draw a phase, so I didn't. But as I said, I've chosen atoms, in particular free atoms, but people also use ions. There's a couple of groups at Waterloo doing some new work with that, molecules, artificial atoms. There's lots of people doing different things. So why are atoms good? Well, it's sort of because they have this really nice structure that I alluded to before. So I'm going to talk about rubidium because that's the atom we use in my lab, rubidium-87 in particular. And so these are the levels I drew earlier as sort of cartoons, but they're real in our labs. Instead of, you know, 6 nucleons here, 7, I can't count quick. We actually have 87 nucleons. That's the mass of the rubidium atom here. So there are actually 36 inner electrons, but there's one single outer electron. And it's that single outer electron that we can control by interacting it with lasers and other optical fields. So we can sort of break that atom into different energy levels, as I mentioned earlier. So we have ground state levels and excited state levels. These different ones have different energies because of something called spin orbit coupling. So the fact that the electron sort of classically sort of spins around the atom, and when it has well, it orbits around the atom, but it also has spin. And when the spin and the orbit are lined up, they have one energy, and when they're anti-aligned, they have another energy. So we can get different energy levels within the atom. This is at 384 terahertz. That's the frequency of a laser. But if we look closer, we can sort of zoom in, and the atom sort of has other transitions. So we can have a microwave transition due to something called hyperfine interaction. I won't jump into that. And we can get even finer transitions using radio frequency. So sort of about a megahertz of energy level differences as we zoom in even further on these energy levels. And these energy levels happen because of the interactions with that electron and external magnetic fields. So we have a lot of control, and we can also control these atoms with different frequencies, which is fun. So you can use lasers, we can use microwaves, we can use RF, and we mix all of these things in the lab to do the different experiments that we want to do. These atoms in particular are really easily controlled, and it's because they look a lot like hydrogen. So this slide is maybe a little bit beyond the undergraduate level, so I apologize for that, but I wanted to throw a few formulas at you. So the 2 levels on the bottom here, we can connect with microwaves, and that depends on an oscillating magnetic field. These optical transitions are very much stronger, and they depend on an electric field. And this actually has to do with the fact that electric fields are much stronger than magnetic fields, and also there's other reasons, but that's one of them. And so we want to, in particular, we work with these two different kinds of transitions, either on this laser transition or these microwave transitions here. So we sort of have three different things going on in the lab. I wanted to sort of dive into all three very briefly in just a slide each, and then I'll go into more detail. But one thing that we use is that we use these strong optical transitions. So from both of these ground levels, there's sort of two separate optical transitions that we can use. And we use that for a quantum memory. Oops. And so the quantum memory is the idea that we send light into the atoms, and then we write information into the atoms with light. So we kind of can hold on to that information inside the atoms for some amount of time, and then later we get it back. And so we do that by controlling these two optical pulses, and I will tell you in detail about that. A second thing we do is we interact microwaves and optics at the same time. And so we have a little microwave cavity here where we have a cell full of atoms inside, and we interact both of these fields at the same time. And we can do some fun things with that. So I'll tell you a little bit about that. And then the third thing we do is actually incorporate all three at the same time. And we do what is called a non-Abelian dynamics. Sorry, my meeting controls have hidden my, let's go backwards. There we go. Non-Abelian dynamics, which is a sort of interesting fundamental topological quantum mechanical phase that we add by manipulating these three levels all at the same time using two photon laser transitions. We control the phases of the lasers and the external magnetic fields that sort of tune these energies up. And what that means in the end is we end up with this system where if we go change our parameters one way versus changing them the other, even though we end up in the same place, depends which path we've taken. So the physical outcomes depend on the path. And this is interesting because it's saying that the topology of space is different depending on which way we go. And there's actually some interesting applications for quantum computing in this as well. Again, a little bit beyond the amount of time I have with you today, so I'm going to skip that one, but I just wanted to give you a flavor. So yeah, we have a lot of different things going on in the lab. I'm only going to talk about a few of them, but I just wanted to say, you know, part of what we do is work with Bose-Einstein condensates to do quantum simulations. So I'm not going to talk too much about that today. That's related to these non-Abelian phases. We have a project in atomic quantum memory. That's what I'm mostly going to focus on. We do some microwave atom optics, which I'll talk about a little bit at the end. And then we're also looking at building new kinds of quantum systems that incorporate ultracoldness. And more recently, we're thinking about something called a tweezer array, so we can build a sort of small scale quantum computer in our lab as well. So how do we get to this quantumness? We can have atoms that can, you know, buy a chunk of rubidium metal, but it's not a quantum object. To get them quantum, basically we need to make it cold. And the reason we want to make it cold is because we have these energy levels just represented in cartoon here, but that energy splitting is very small. So what we need to do is get the thermal energy, the energy of the temperature, to be even smaller than that in order to have control over these energy levels. So that's just a very simple way of thinking about it. And to do that, we use something called laser cooling. So this little pink blob in the middle of our big experiment here, this scale is that's 30 millimeters, 3 centimeters across there. So we can zoom in, and this is a little cloud of atoms about 1 millimeter or 2 across, and it's about 1 billion atoms that have been laser cooled, a few microkelvin above absolute zero. So I do want to spend a little bit of time just talking about how we do that. If we think about temperature, really is just an average speed of atoms, the average energy. Then something that has temperature is just, you know, a measure of how much these things are moving. And so if we think about different temperatures, it's actually really nice to think about temperature on a logarithmic scale, where you go from, you know, the temperature of the sun. Of course, things can be much higher in plasmas, for example, or in the center of the sun. The surface of the sun is about 6,000 Kelvin. Down through room temperature at 300 Kelvin, and then say the cosmic microwave background at about 3 Kelvin. So that spans maybe 1,000 degrees in temperature here, but it's also a factor of 1,000. So we should really think about temperature on a logarithmic scale. And so if I divide by 1,000 again, 1,000 again, I'm getting closer and closer to absolute zero. But in thinking about it in this division way, it makes sense it'll never get to absolute zero, as you know that you can't. So if we want to get colder than outer space, we need to do something artificial in the lab. And there's many different techniques to get cold. Cryogenics, like liquid nitrogen, which maybe you're familiar with, is one way. Using liquid helium in a cryostat can get you to about 1 Kelvin or a little bit below. But to get much colder, you need other techniques. So dilution refrigerators are one way where you can get down to about 1 millikelvin. or thereabouts. And then if you want to get colder than that, we go to much smaller samples of laser cooled atoms where we're in the sort of tens of microkelvin range. And using further cooling techniques, we can get down to Bose-Einstein condensation where we're at, say, 100 nanokelvin. And so we do this in our lab every day now. And this seems pretty extreme, but really we should think about temperatures in terms of velocities, I think. And so for the rubidium atoms we use in our lab, we're really talking about sort of at room temperature as actually 300 meters per second. And then as you get colder, we're really talking about slowing the motion down. So as we go colder and colder, there's actually a square root in this problem. And what it means is that when we get down to these very coldest temperatures here, we're really just talking about moving at a centimeter or a few millimeters per second. And as an experimentalist, I can say, okay, well, you know, this temperature sounds crazily cold, but really the speed isn't crazy. I can think about something moving in a centimeter per second or a millimeter per second. How do I do that in the lab? So the way we do it is actually by transferring momentum. So if we think about, you know, how to slow something down or how to change its momentum, we can think about this idea of a recoil. And so, whoops, someone's spraying water in my window here. So what we're going to use is actually the momentum of light. And the idea that momentum has light is not new, but it is a nice way to use it. So the softball here represents the light, and the catcher represents the atom. And so when the catcher catches the ball, she's going to feel a recoil sort of backwards. So that momentum of the ball is going to transfer to her. And even though the mass of the ball is much smaller than she is, it has a lot of momentum because it's traveling quickly. And so she still feels that recoil, although she's still much bigger than the ball and she can stop it. And so it's the same kind of scale that we're going to think about when we send light at an atom. As I mentioned, this idea is not new. Light has been known to have momentum for a long time. And one of the first pieces of evidence for that was actually the tails of comets. So when comets are orbiting the sun, especially as they get close to the sun, the ice in them starts to melt, and some of the gases are released, as well as some of the dust that was trapped in the ice. And it turns out that the gases always point away from the sun. So you can kind of see this gas tail pointing directly away from the light. And that's because the momentum of the photons coming from the sun is being transferred to the gas molecules and pushing them away. It's doing the same thing to the dust, but the dust actually has a larger mass. And so the momentum transfer is the same, but the velocity transfer is not as great. And so the dust kind of trails behind with this arc, characteristic arc that you might have sort of seen for comets. And so this, you know, the shape of the comet is really evidence for the momentum of light. Now, how we use this to get atoms cold, we send light in at our atoms. And if we do that, it's going to transfer its momentum. So if we just think about atoms here with 3 different colors of light, where here the frequency is sort of too high compared to the energy levels of the atoms. Here it's just right, and here the energy level is too low. It's got too long of a wavelength. So we send that light through. If it's not resonant, the light just passes through, but if it is resonant, it's going to excite the atom and also give it momentum. So you have to conserve both the energy and the momentum in this process. And so the atom, which was not moving before, is now moving, and there's no light. So we sort of conserve that momentum in that process. So how do we use that for cooling? What we actually want to do is consider the Doppler effect. And so this is very familiar from, you know, fire trucks. This is a book that I used to read. My daughter, she's getting a little bit old for this now, but of the fire engine racing by, and the sort of woo-wee sound that changes as the fire engine moves past you is this evidence of the Doppler effect that we all know. So the same thing happens with atoms. Atoms also experience the Doppler effect, and they experience it with light. So as the atoms are moving away from the light, here, what was too high of a frequency before is now sort of stretched out. So the atom's moving away, it kind of pulls that light apart, and now that light is resonant with this transition. But the same thing happens for the other 2 frequencies as well, and now they're both too low and not resonant. So the light's going to pass through on the bottom 2, but it's going to absorb on the top one, and it's actually going to increase the momentum of this atom. So that is not what we want. Unsurprisingly, I showed you the thing that's bad first. So what we want is for the atoms that are moving towards the light, now the frequency that's too high is way too high. The one that was just right before is still too high. And the one that was too low has now come into resonance. So as the atom is moving towards this, it sort of sees the waves come faster, and so it has moved into resonance. And what happens here is that the atom that was moving to the left previously is now slowed down. And so its momentum is less, represented by a shorter vector. I've exaggerated the effect here, but we see that. And sorry, the light should pass through on both of these here. So this is the effect that we want on the bottom here to achieve cooling. We want the atoms to absorb light only when they're moving in the opposite direction of the light. So for a gas of atoms, what we can do is basically just put a bunch of atoms in a box, and then we send light in actually from all 6 directions. So there's beams coming in and out of the page here as well. And what happens is that, say this atom that's moving towards the left is only going to be resonant with the atoms that are moving towards the right. And likewise, for each of these atoms I've got drawn in the 4 different directions, they're only going to absorb the light that's moving in the opposite direction to what they are. And so eventually they're going to slow down really to very slow speeds, to these millimeter per second scale speeds. And so it's a passive cooling technique that just by turning on these lasers, you can sort of cool these atoms down so they're moving very, very slowly. And this is very close to the regime of being able to see these quantum effects. So to do this in the lab, we need to isolate the atoms from the environment. So here we've got a big vacuum machine, and you can see a few different glass regions here where the air is removed, but now we can sort of introduce the atoms that we want. Those are rubidium atoms, and then do some cooling. This is when I first built the system 8 years ago now. And it's pretty naked. It doesn't have many other things around it. So eventually we have to add some laser light. We add some magnetic coils to control the magnetic fields as well. And eventually you end up with this ultra cold gas of atoms, which I've showed you many slides ago now inside of these coils. And this is actually the glass box. You can see the edges of it here. So let's get on to some last physics. I'm not going to, maybe I'll just talk about the quantum memory since we don't have, I wanted to leave some time for questions. So give me maybe 10 minutes and I'll try to wrap it up here. So the atomic quantum memory comes back to this picture of quantum communications and, sending information from one site to the other. Memories are actually going to be one of the first technologies that we need in order to make this practical. And whether that's, through ground-based links like in fiber, which I draw in blue because they're blue in my lab, or through satellite-based links, which we're also starting to think about. One of the important things is for timing, we need memories to be able to synchronize our signals from different places. So there's going to be many components of the quantum internet, I should say, and memories are really just one. So we might think about, in one side of our quantum network, having our quantum computers that do our banking, that have our secure communications, or maybe they're doing a calculation about astronomy that we want to send to another telescope somewhere else. We have some kind of quantum sensors, maybe that we want to detect signals and send them to other places as well. And so we're most likely going to do that by light, because light is a very quantum system and it carries information with very little disruption compared to most other quantum signals, whether that would be through microwaves or RF or electronic signals. So optics, and that's really because photons don't interact very well with matter, and that's a good thing for most things, but we do need to have other systems that can interact with them if we want to manipulate it. So some of the other technologies we'll need are things like single photon detectors, and people are working on making those chip-based rather than sort of a whole big cryostat right now. And quantum memories, which is what I'll talk about. And another technology we might want to talk about is a quantum transducer, which is a little bit related to the microwave work that we do in our lab too. So with this quantum memory, why might that be useful? Well, say you have some single photon sources. And one of the things people often want to do is sort of at this sort of place in the network, you might want to build something called a repeater. And so a repeater is useful because you can send information in a quantum mechanical channel without loss. And so imagine in this repeater station here, you had two single photon two entangled photon sources. So you send photon A and B out this way, and then photon A and B out this way. And to make this work, what you actually want to do is measure A and B together in something called a Bell state measurement. So you send these two photons in here, you measure them, and you see what you get. This measurement actually acts to entangle the two photons together. And that means if you entangle these two, then A and B are also entangled. But if you send one of these to the west and one of these to the east, now you're sending a pair of photons that sort of is entangled with each other in these different directions. The role of the memory here is very important because as I send this one from the west or one from the east, then I know the timing. And so a lot of these processes are actually random in the kind of detectors that we're using today and the kind of sources. And so the ability to hold on to our information and then send it later allows us to get the timing right so that we can actually do these measurements at the right time. So that's just one possible application of a quantum memory, but there are many. Of course, if we build real quantum computers, we need a way to hold on to that information, and some kind of memory is going to have to be there as well. So the basic idea with the memory is that we have some kind of material system. In this case, it's going to be atoms inside of a vacuum, which is this sort of little box I've got. We're going to send some kind of input signal in as light, because light, again, is sort of the good medium for transferring information through the network. And then we'll have some other kind of control mechanism. In our case, it's going to be a second beam of light. Send those in, hold on to that information for some time, and then after a desired amount of time, we want to get it back out. So we have our output signal on the back end. And this is just sort of a cartoon picture of how that all works. More mathematically, the question is, how do you transfer information that's sort of in this superposition or qubit form that's in the photonic degrees of freedom, that's light, or some kind of electromagnetic field, to a more permanent storage location where this superposition will live for a long time? So our question is really, how do we go from being in these photonic degrees of freedom, having a superposition in the light, sort of nothing going on with the atom, to make it sort of empty the information from the light degree of freedom and put it into the atomic degree of freedom? So we use a technique we call the Ultracold splitting or AC Stark shift method. I'll go into just some sort of cursory details of that. We basically start with this idea where we have a quantum system that has three distinct levels, and these two are what we call ground states, and this is an excited state, and they're both connected by laser lights, represented by these red arrows here. These transitions are what we call forbidden. So basically, you don't get any spontaneous mixing. So if you're in this level, you don't sort of just drop down to this G level. They're both really near in energy, and so if you write a superposition between G and S, it's going to stay there. And so that makes these good storage levels. And what I want to do is create a superposition between those two levels that I can retrieve some later time. And so how do we do that? It turns out that if we apply light, we can't directly couple these. So the fact that they're good storage levels means that they're also hard to couple. And so these kind of come hand in hand, but we can couple them sort of with this intermediate excited state. And so what we want to do is send information, which we'll call the sort of p hat, in here, and then we'll sort of transfer that part of that information from the E branch down to the S level here. And we're going to do that with our control field. So we sort of think about this as the information that comes in, and this is the control field. And there's a lot of mathematical dynamics that go on behind here in something called the Maxwell-Bloch equations. This is an approximation of them, but the approximation is basically saying that if you have this polarization coherence, what we call it, and the spin coherence, which is sort of saying how much superposition do we have here and how much superposition do we have in S, then what's going to happen is that this control field does something called Rabi flopping. So if we just had two levels and we shine a laser on them, what happens is that if you have population here, it'll transfer down to S, but then it'll come back to E and back to S and back to E and back to S. And it actually does this as a sinusoid, and this is called Rabi flopping. And that's a sort of characteristic of quantum systems. In our three-level system, we're going to do that. But what we're going to do is sort of create a superposition between G and E, and then let that Rabi flopping start. So now the E turns into S, and now we'll have a superposition between G and S, but it'll go back to E and back to S and back to E. So we sort of go between having superpositions here, which is represented by this P number, and having superpositions here, which is represented by the S. And then the light couples to P, so we actually represent that by the red one too. So these equations explain these dynamics, and it's just showing that there's a sinusoidal oscillation that is out of phase. So if we go from P to S to P to S, we can go back and forth with that excitation, and every time the P is excited, we get some light associated with that. So the way to make a memory out of that is basically to shine your light on. Some of it's going to be absorbed. This blue line represents just keeping that control field on. And so then after some time, we basically excite that. So we send in the light with the pink here. Sorry, the color has changed a little bit. The first polarization coherence gets excited, that flips into spin. So we have storage, and then it flips back into the polarization, and that couples back to the light, and then we'll get light back out. So that's in sort of one period of this Rabi oscillation. And there's a little bit of echoing happening. So it kind of keeps going even though the amplitude decreases, because we've actually added a few of the realistic loss parameters into the simulation. What we can do to make it a memory is actually turn off that coupling between the E and S levels at exactly the right time. So we let the light come in, it absorbs, it transfers over to the spin coherence, and then we shut it off. And in principle, we can shut it off for as long as we want, and then turn it back on again. And once we turn it back on again, we just begin those dynamics that we paused, and they start again. So in principle, we can hold on to this infinitely. In practice, there's always something going on in the lab that's going to make that imperfect. So we can see how long we can hold on to that for. And just one detail with this system is that we can actually, we don't have to use these square pulses, we can use rounded pulses, and we can kind of design the shapes of the input and output pulses, which is nice. So in the lab, what we do is we send those two beams of light into an ultra-cold gas of atoms here, which we call the magneto-optical trap. It's related to laser cooling with this magnetic field on. And then we detect the signals out on the other side. So we have our signal and our control beams represented by red and blue here. And we can do this. So this is from actually somewhat later experiment where we can send in light at a very low photon number. So we send in on average 0.1 photons per pulse, which just means it's a very low light level, which is sort of in the quantum regime. So we send that light in, and then 200 nanoseconds later, we recall it, and we find that we actually get very low noise. So this is the red signal that we want, and the blue and green represent the noise level. So they're very much lower than the signal that we want. And so we're able to sort of pull that photon out again sometime later. So this is quite a short times 200 nanoseconds. We can actually hold on to it for quite a bit longer in our more recent experiments. Another thing we can do with this system is something called temporal beam splitting. So it allows us to manipulate the quantum information over time. And what I'm showing here is that we can think of this system as a beam splitter. So if I send in my original signal with this red beam, it transforms into a spin wave. So that's what we call the spin storage. And it's like a beam splitter reflecting, basically changing modes. We change from electric field to spin, and then we store it. And then later on, I apply the thing again. So the application of my control signal is the beam splitter. And then that flips back from spin to the electric field. So I store it, I send the light in, we store it for some time, and then we get the signal back out after a later time. So this is an analogy to a beam splitter. It's not an idea we made up. We borrowed it from some friends at Imperial College. But what's nice about this is that our memory uses it. So what you can do is actually write a signal in and then set it up so that your readout actually varies in amplitude. But in the end, what it means is that you can get, say, 4 pulses out at different times. So we've got the input here and then 4 different output pulses that represent that we can have sort of a superposition of, we send only 1 photon in and we apply these 4 pulses, we don't know which of these outputs the photon comes out in. And so we can create a superposition of the photon being in all 4 outputs at the same time. And so this scheme is not only good for storage, but allows us to manipulate the photonic states and their quantum degrees of freedom all at the same time. So finally, we did some experiments where we actually applied these not only to laser cooled atoms, but to much colder atoms that had been Bose condensed. So this is a very cold sample of gas at around 200 nanokelvin. And here we just are showing the same kind of plots. We send some light in, and then we get it back some 200 nanoseconds. This is our nice sort of demonstration time, get that light back out. But we can see that as we change the temperature from about 6.2 microkelvin down to 80 nanokelvin, you can see that the time that and versus efficiency, so that the efficiency, which means how much signal we're getting back out, basically, is much greater when the atoms are colder. So the colder the atoms are, the more perfect their quantum states are, and the longer we can hold that information for. So that's what we're representing here. So the next steps for these sorts of experiments are to continue to improve our performance. So our storage times are still kind of in the microseconds. We'd like to get them out to the millisecond range. We also want to improve our efficiency. So right now, our best efficiencies are around 30–35%. We'd like to get that above 80, and also to work on bandwidth. So I didn't really talk about it, but this scheme is very good at bandwidth. So we have very high bandwidths, which means we can do things rather quickly. But we'd, of course, always like to improve upon that. And that would just make it a more practical information technology, the faster you can do things. The last thing I'll mention is that we would also like to engineer different connections to quantum networks. So I talked about, using these in a real quantum network as a repeater station, and we would like to sort of start demonstrating that by hooking these into real fiber networks in sort of the urban scale. And we're also talking with and working with the team who is launching what's the first Canadian quantum satellite, which should launch next year. And it's actually very much compatible in terms of the wavelengths with our quantum memory. So we'd like to put a quantum memory on the ground and use it to communicate with the detectors on this quantum satellite. So that is to come. Hopefully next year we'll have some more to say about that. So I'm running out of time, so I'm just going to skip through this last little section on microwave atom optics. But just to say that actually we use warm atoms in the system, and it's a nice little small scale technology where we're looking at interacting microwaves and laser light together in the atoms to develop technologies that are maybe more portable for things like magnetic field sensing, and also quantum transduction, where we could take microwave signals and change them into optical signals. So I'll just quickly go through this and come to my conclusion, which is to say, I hope you've sort of taken away from this that I think quantum technologies are a new path for different computational tasks, both in communication and in sensing as well. Quantum effects come about when we make things cold often, and one way to do that is through laser cooling to make the kinds of ultra-cold quantum gases that we use in my lab. And finally, I got to talk a little bit about our quantum memories, which we use to store and distribute quantum information, which is a very important task in quantum communications, and eventually will be used as well for computing. And we're actually, with that last sort of hybrid project that I mentioned very briefly, thinking about ways to interact this kind of system with a new kind of quantum computer called a neutral atom array. So for my last slide, let me just sort of thank everybody who actually does this work. This is the most recent group photo. We're missing one person, but it's always hard to get this many people together for a photo these days. So let me say thank you to them, and I'll just leave this up for a moment with my website, and my email address can also be found down at the bottom here. So thank you so much for your time, and I'm happy to take some questions for the next few minutes here.
Awesome. Thank you very much, Dr. LeBlanc, for her wonderful presentation on exploring quantum technologies with atoms. So before we move on to the Q&A, I would like to encourage you, all of the people here, to please register for our next session of the Physics Hour with Dr. Jess McIver from our very own UBC. She is giving a talk on gravitational waves, and the title of her talk is basically gravitational wave astrophysics, a new frontier. So for those of you that don't know, she was involved with the team that is LIGO, which detected the gravitational waves when it was these two black holes merging. Okay, so that should be it for the recording.